Hello, we're very happy to have Jennifer Park here today, and she will tell us about Diophantine problems and undecidability. And how do you like people to ask questions during the talk?
Just you can just butt in. I would be very happy to be interrupted.
Okay,
I
so
won't be, yeah, I don't think I would be able to see all the hands going up, so you should just stop me.
are you going to follow the chat?
Oh, I don't know how, I don't have the chat open, so it
Okay,
would be
okay,
better if you
that,
just
that's
ask. Or if somebody sees the chat, then you can just stop me and ask or something.
okay. Sounds good. So yeah, go ahead.
All right. Actually, I just opened the chat. Okay. All right, so thanks for the invitation. I'm a number theorist, but I guess for some of the time, I also do logic that's basically kind of motivated from number theory. So I thought I would talk about Hilbert's 10th problem just because I think it's a pretty small area that not that many people do research in, and it's really interesting. So I thought I would start by asking you guys questions. I don't know if this is like a good thing, but maybe you can just like type in the chat or, actually like say something. But I was going to ask you a bunch of questions first. So the question is going to be this. So does the polynomial, and then I'm going to like plug in random polynomials. And does the polynomial have a solution in the integers? Okay, so that's the question. And I'm going to give you a bunch of polynomials, and I would like you to answer either yes or no, depending on whether you see an integer solution or not. Okay, so that's the game. So let's start with something really simple, like x plus 3 is equal to 0. Okay, so does it have an integer solution or not? X is equal to minus 3. Yes. Okay, great. So people are listening. So that's really easy. Okay, so this is yes. Okay, and then the next slightly harder question. So 2x plus 5 is equal to 0. Does it have an integer solution or not? No? Okay, so definitely not, because the only solution is going to be minus 5 halves. And I guess that's not an integer, so it does not have an integer solution. Okay. When I say a polynomial, I don't necessarily mean that it only has a single variable. So I could also ask questions like x plus y plus z is equal to 0. So does it have a solution or not in the integers? Yes, and there are lots of different solutions, right? So for example, 0, 0, 0 is a solution. You can also do like 1, 1 minus 2, and like, many, many like infinite times infinite, countable times countable solutions or something like that. So lots of solutions. Okay, getting a little bit harder. So x squared minus 14x plus 49 is equal to 0. Yes or no? Yeah, lots of yeses because we all know how to factor, and 7 is the only solution, right? So far you guys are doing great because this is basically what I want to automate, kind of. Okay, so let's see how far we can go. How about x squared plus 1 is equal to 0? No, because any integer squared is going to be positive. So positive plus 1 is always going to be positive. So it's never going to be 0. The only solution is I, right? So no solutions here. Okay, getting a little bit trickier now. So now I'm going to go back to multivariate question. X squared plus y squared minus z squared is equal to 0. Yes or no? Yes. I can see like it's like a little bit slower. So these are the Pythagorean triples, right? So you can do something like 3, 4, 5 or 5, 12, 13, and things like that. So again, this is a yes. Okay, getting a little bit harder. So I don't know how many people are going to be able to answer this one. So let's try x squared plus y squared plus z squared plus w squared minus 2026 is equal to 0. Does this have an integer solution or not? Oh, I'm getting a bunch of yeses, but there was a question mark as well. Okay, so does anyone know why it has an integer solution? It's true, it has integer solutions. Ah, okay, so this is exactly your topics. This is Lagrange's four squares theorem. Okay, so four squares theorem, oops, four squares theorem basically says that any positive integer can be written as a sum of four squares, right? So, oh, somebody even found the solution. Okay, I was not looking for that, but that's great. I actually didn't notice. So any integer, positive integer can be written as a sum of four squares. Okay, so that's great. Okay, so how about this one? X cubed plus y cubed minus z cubed. Ah, now I'm tricking you guys though. Well, okay, so what is it? Okay, I'm getting a yes. And x cubed plus y cubed minus z cubed is equal to 0. Fermat's last theorem says that it has no non-trivial solutions, right? So you can do things like 0, 0, 0 or something like that, or even like 1, 0, 1 is a solution and so on. But now let's try this. Okay, so now I'm going to square this. Still, it has solutions, but now I'm going to do something weird. So I'm going to do plus, and then I'm going to do another equation. So I'm going to do x minus 1 minus t1 squared minus t2 squared minus t3 squared minus t4 squared. I don't know if you were seeing what I'm getting at. And then now I'm going to do y minus 1. And I'm going to do something similar like s1 squared up to s4 squared plus z minus 1 minus, I guess, u1 squared minus u4 squared is equal to 0. Okay. Does anyone see what I'm trying to do here? Do you know if this has an integer solution or not? Yeah, okay, so Marcus definitely said something that's very useful. System of equations can be written as a single equation by squaring and adding, because if I were looking for integer solutions, then all the squares basically have to be zeros, because I know that all of these terms are either going to be positive or, 0. So if this were equal to 0, all of the things inside the squares have to be 0. Okay, so this is the system of equations. So I'm asking for a solution in this, like, the Fermat's last theorem type thing. And then I have three other equations. So do you guys see what this equation is going to do? It has something to do with Lagrange's four squares theorem, obviously. It means x is bigger than or equal to 1, right? Because x minus 1 can be written as a sum of four squares. So that means that x minus 1 is non-negative. Okay, so that means that x is bigger than 1. Okay, so it forces x is bigger than or equal to 1. So what is the answer? So this is true Fermat's last theorem, right? So by Fermat's, I can't write FLT, right? So Fermat's last theorem, the answer is now no. Okay. So there are lots of things that you can do with these kinds of equations to sort of be able to, I guess, express a lot of the things that you kind of typically talk about in math using polynomials. So I guess that's sort of what I wanted to illustrate. So I guess this is the question that I'm going to be asking. Okay, so the question is going to be something along this line. Basically, if I give you a polynomial, even harder ones than these ones, will you always be able to answer yes or no, depending on whether it has an integer solution or not? Okay, so this is the game that we're trying to play. But I guess the point is that somehow all of these things, all of the examples that I gave, you kind of had to go through a different process, right? Like, there was not a single process that you could kind of plug in the polynomial to and get an answer. But is it because like we're like, not smart enough to actually find the program, or, is it just how it is? Are you allowed to introduce a term like x, y, into your polynomial? Yes. So you're allowed to do sort of like anything, you can have any number of variables as long as it's finite. And then you can do like, the addition and multiplication. You can take exponents, but not x to the y type thing. You can take fixed exponents, and you can do all of that kind of stuff. So like whatever you usually see as polynomials. Okay. So there are like really wide ranges of polynomials. I'm not even telling you how many variables I have, right? So, I'm just basically asking. Okay. So, and this is really the content of Hilbert's 10th problem. Okay. And it literally just asks this question. Okay. So does there exist an algorithm? Okay. And, algorithm, I'm going to put a star here because we have to talk about what an algorithm is, such that, and an algorithm really, I guess, you just kind of like, when you kind of learn computer science for the first time or something, you kind of see the algorithm as a black box, right? So whatever this is supposed to be like your algorithm. And the input is going to be some polynomial. And because I'm going to be asking about integer coefficients, if I have like irrational coefficients or like, imaginary coefficients, it's just not going to work. So I'm always going to ask for polynomials with integer coefficients. If it were rational, you can clear the denominator, so this is not a big deal. So I'm always going to input a polynomial, like, one of these things, into my program, whatever that is. And then the output is either going to be yes or no, right? Depending on if it has an integer solution and no otherwise. Okay, so this is the question that Hilbert asked. which is, like very reasonable given like what we've been doing. And, people have been solving equations for years, I guess centuries or something. So this is not a crazy question, but the crazy part is this. I know that you guys are like, not, is this question solvable? Yes, I'm going to give you an answer and I'm going to give you sort of I guess a proof, a sketch of the proof. Okay, so this is the rest of the talk, or like, 90% of the talk. Okay, so the really cool thing about this, I mean, this is a really natural question, especially now. But I know that you guys are really young and you guys haven't really thought about it, but there was a time without any computers. And in Hilbert's time, not only did they not have a phone, they like literally just didn't have the concept of a computer. So this is like a really interesting question to ask because they really didn't even know how to sort of like fully make this question rigorous. Okay, so okay, somebody proposed a quantum algorithm to solve Hilbert's tenth problem. Maybe someday quantum will work, but I'm kind of skeptical for now, I guess. 2001. Okay, I actually didn't know this, but I think in 2001 quantum computers were like useless, right? So I don't actually know. I would have to go and like actually think about this. So I'm not really sure. Okay, but anyway, so the really cool part about Hilbert's 10th problem is that, they were asking questions without sort of like fully defining exactly what they mean by a computer. Okay, so then we can kind of think about, what does it mean to have a computer, right? So like, what would the people in the, I guess, what is this, 20th century, what would they have envisioned if they were talking about a computer? Because, it really did not exist. So let's kind of think about what are the sort of the basic requirements that we need if we wanted to build something like a computer, right? So what is a computer? And what kind of information or what kind of restrictions do we need on the computer? Well, first of all, it has to take an input and it has to give you an output, right? A computer literally means that it's computing for you, right? It's like a thing that computes. So we should have an input and an output. So there are going to be a bunch of restrictions that I'm going to place on the input and output. So the most important thing is that both of these things have to be finite. Okay, so if I gave you like a really like an infinite string of input, the computer is never going to be able to kind of read everything and actually like have the time to like output anything, right? So like I want the input to be finite, I want the output to be finite so that, we have some like, some kind of a restriction and, some kind of like an expectation that, something is going to happen. Okay, so that's really easy. And then the input and the output, I'm going to assume that they're either in binary or they're just encoded in the integers. Okay, so these are assumed to be either binary or in the integers. And why can I do that? I don't know how many of you guys have thought about these like sort of the problems of infinity and like countability and uncountability or something like that. But basically what I'm kind of getting at is that, a lot of the concept of infinity, it really kind of, I guess in real life, often we're only kind of thinking about a countable number of things. So the point is that there are only finitely many characters in the world. Like I know there are lots of languages and like, also emojis or whatever, but there are only finitely many of them. So whatever that is, I can sort of number them all. And whenever, even if I'm taking like combinations of them, as long as the input is finite, they're only going to be sort of finitely many things that I can make. Well, yeah, they're kind of coming from finitely many characters. Okay. So then if I were kind of thinking about all the different inputs that I can make from these finite set of characters, that's just countable. So that means that I should either be able to kind of express them in the integers or express them in binary. Okay, and if you didn't get that, I don't know. I guess we'll just kind of take for granted that I'm always just going to be like inputting either an integer or like something in zeros and ones, basically. Okay, does that make sense? Are there any questions that I can clarify before I go even further? Does it have to be binary specifically? No, it does not have to be binary specifically. It can be integers. It can be in like ternary if you wanted to like think about the quantum stuff or whatever. And all I want is just like some very like well-defined way of just entering something into the computer. Like, the very basic model of computers that we're going to be talking about. They're not so sophisticated. And if I wanted to kind of model them, I mean, you're going to see one very soon. The way you model them, like, it's just much easier if you have like a very small set of inputs or like if you can kind of quantify the inputs in a very simple way. So binary is easy because you're either reading 0 or 1 at any given time. So that's really useful. Okay. But I mean, yeah, even if you had like a million different characters for each input, that's fine in real life. But as long as we're discussing something like on paper, I think it's much easier if your input is either one of 2 things or one of like 10 things or something like that. So that's why I'm doing this. Okay. Okay. And then the other thing that a computer should do is that it has to be sort of, oh, sorry, there's a question. Are you assuming that the algorithm is finite? Yes. So I'm going to get there. So that is a great question. And that is another restriction that I want to place on the computer. So we might as well just write this, I guess. Okay. So the algorithm, and I'm going to sort of like conflate this with like a program or whatever. So the algorithm itself have to be described in finitely many characters, or in finitely many characters. Because I guess the idea is that, you kind of want to physically build a computer or something. So then if it's infinite, then like, how are you going to do this, right? Yeah, if the algorithm is defined to be not allowed to be not finite, you can just check solutions until you find something. It's kind of true, and I will kind of like run into something like this, but I think the program itself has to be finite. I mean, like, the inputs, yeah, anyway, so like we'll get there, okay? Yeah, so the machinery itself definitely has to be finite. Okay, and then the other thing that you really need for the computer is that no matter how many times you run this on the same input, you have to get the same answer, right? Otherwise, it's just some kind of a random answer and like it's not going to be reliable and things like that. So, so each operation has to be like robust, I think maybe they say, but I'm going to say well-defined because I'm a mathematician. Each operation should be well-defined. Okay, and by well-defined, I really mean like no matter how many times you run this, as long as you feed it the same input, you should always get the same output. Okay, so these are sort of the most basic requirements for a computer that you need. And when you kind of take these kind of ideas and try to build a computer, you're going to get something like this. Okay, so here's a computer, a very like primitive version of computer. I think that I mean, it's still in existence, but I think the idea maybe came out in like the 30s or something like that. Okay, so then here I'm going to assume that my input is in binary. And what my computer is going to do, I'm going to instruct my computers to start reading it from left to right. Okay, so I mean, in binary, I guess it's the largest digit first, and then you're just going to keep reading it. Okay, so read from the largest digit. Okay, so I'm just basically trying to build something that satisfies all these restrictions that we kind of came up with. Okay, and so every time I read an input, I'm either going to read a 0 or 1. Okay, so this is where I start. And if I see a 0, I'm just going to loop. Okay, so I'm just going to stay at whatever this is. Okay, so these are called states. So when I read 0, I'm going to stay here. But when I read 1, I'm going to go elsewhere. Okay, and I'm going to sort of like mark this as a yes state. Okay, so if I read a 1, then I go to yes. Okay, yeah, we're getting there. Okay, so you know what I'm talking about. Okay, so then if I read, so from this state, so I've read my first letter, and then I'm either at this state or this state. Okay, and then I'm going to read the next letter. And if I read a 1, then I'm going to stay at this state. But if I read a 0, then I'm going to go elsewhere. Okay, so I guess I will just go back here. Okay. So when I finish reading, I guess my input, I'm gonna end up in either this state or this state. So let's just call this like a no state. And can you guys tell what kind of operation this machine is doing? It's a parity. If it ends in 1, then it will end up in the yes state. And if it ends in 0, it'll get to the no state, right? So it means that this machine accepts odd numbers in binary, and it rejects the even numbers. Okay, and this does exactly what we kind of like described. So this could be taken as a definition of a computer. Does that make sense? So this is called the deterministic finite automaton. I think someone was asking whether if it was a DFA, and that's exactly what it is. So this is called deterministic, which means that it's well defined. Like, every time you read something, like there's a very there's like a very specific thing that you have to do attached to that input. And it's finite, which is important, and automaton, which I guess was the name before computers came in. Okay, so this is called, so often this is called a DFA. And this actually has a pretty serious limitation. Okay, so what is the limitation? So the problem that I'm going to state as a theorem. So there does not exist, so no DFA. And I mean, there are like lots and lots of different DFAs, as you can see. I mean, I can just add a bunch of nodes and, it can do a lot of things, but no DFA can accept precisely the inputs of the form zeros followed by ones, and they have the same number. Okay, so if I asked you whether you could build a DFA that accepts 0, 1, 0, 0, 1, 1, 0, 0, 0, 1, 1, 1, and so on, and nothing else, that does not exist. Okay, so this is not a very powerful computer because, it would be really nice to do something this basic because it's really just kind of comparing the size of sort of two different things, and it can't do this. And I'm going to prove to you why this is not possible. Okay, so suppose that such a machine existed. Okay, so suppose such a DFA existed. Okay, and then remember that DFA, like the F is for finite, so there are only going to be finitely many states of these things. Okay, so now I'm going to feed it a really long string of zeros and see what happens. Okay, so so consider like a really, really long string of zeros. And in particular, I'm going to have much more zeros than the number of states that I have. So in this machine, I mean, just feeding it 3 zeros is going to be enough, but I could also think about feeding it like a million zeros or something. Okay. So then what happens is that this machine is just every time it reads an input, it's going to sort of bounce around different states. But something interesting happens. So I want to apply the pigeonhole principle. And can you guys tell what happens if I apply this pigeonhole principle? If I have more zeros than the number of states, then at some point, if I consider the states as wholes, 2 states get repeated. Okay, so at some point, the state has to repeat. Okay, so then if this is really long, then by pigeonhole, some states repeat. Okay, yeah, so there's going to be a guaranteed repetition, which means, okay, so suppose that, I had like a 0 here and 0 here, and suppose that my state repeated here. So when I read the 0 here and when I read the 0 here, I'm at exactly the same state. So what does that mean? That means that I could omit this many zeros, and the machine will give me exactly the same result. Does that make sense? Because, I was reading 0, I was at the same state as this one. So why should I even kind of go through this segment? Okay. So then this segment, maybe I can highlight this or something. So this segment, it really doesn't do anything to the outcome of the machine. Okay. Doesn't do anything to change the outcome, which means that I could either omit this segment or I can put in as many segments as I want, and the machine will give me exactly the same result. So yeah, so then I guess somebody figured out, is it the pumping lemma? It's probably the pumping lemma. Yeah, I think it's like a simple version of the pumping lemma. I'm not gonna go there, but if you're interested, you can look at things like this to kind of figure out what kind of things DFAs can do and can't do. But I guess what I'm trying to say, and I think somebody already said this in the chat, is that you can basically insert or omit this segment as many times as you want, and the machine will just basically have the same result. So what does that mean? If I had a string, a bunch of zeros and a bunch of ones, I can break the symmetry by just kind of adding a bunch of zeros on this side and leaving the one that's on this side. So that means that it has to accept sort of the uneven number of zeros and ones. So that's a contradiction. So DFAs are like really not that strong. Okay. So this means that the DFA must accept other inputs, because I can sort of modify by a bunch of zeros, I can modify by a bunch of ones, and they don't have to happen at the same time. Okay, so does that make sense? Other inputs, what do you mean? Oh, yeah, like here, the other inputs. By other inputs, I mean like even if the DFA accepted like, all of these strings, I should also be able to kind of add on a bunch of zeros at the beginning, and it also has to accept that, which is not of this form. So not fully arbitrarily scalable, because there's some like a specific length that it's going to accept, right? So by those lengths, you can always modify these I guess strings, but not, I can't just add in like 3 zeros and expect it to accept that. Okay, does that make sense? Yeah, okay, great. So that's the end of the proof. And by the proof, I guess I mean that this is bad news, right? So DFA is not great. So what do you think DFA? I mean, like our computers now definitely do things like this. I mean, you could probably ask like, I don't know, I mean, I guess ChatGPT is not deterministic, but you could ask ChatGPT and they'll probably tell you that zeros and ones have the same numbers or whatever, right? So it's definitely doable. What do you think is the difference between the DFA and the current computers that we have? What am I missing? Because, I came up with this idea of computers. I built something and it didn't work. And yeah, now you guys are saying now the memory is the thing that we don't have, right? So the computers can actually store, but what the DFA does is it reads an input. And then after that, you can't go back, right? I mean, once you read it, then that's it. Like there's no way to sort of go back to the input. So that's where this idea of a Turing machine came in. Okay, so the Turing machine is basically DFA with a memory. So you can kind of go back and kind of like remember what kind of inputs you read. You can also kind of like, take memos and things like that. So it's a much stronger version of a computer. Okay, so here we're missing memory. And that's exactly what we're going to do to try to build sort of a modern version of a computer. Okay, so this is called a Turing machine. And it really looks primitive because it's very similar to a DFA and we can kind of like, draw everything that it does and things like that. But this is essentially what today's computers are still made up of. So yeah, so what does a Turing machine do? So it's going to have still like some DFA component. Okay, but this DFA is going to do a little more than the DFA that we had before. So attached to the DFA is going to be what's called, I think people call it a head. Okay, and this head is going to kind of like point to a specific place in your memory. Okay, so the memory, you should kind of think of it as like a long tape. And at the beginning, whatever your input is, the tape is just going to kind of like have that written on it. Okay, so I'm not just sort of arbitrarily reading the input. The input will be written on this tape, and then I will be reading the input from that tape. And so every time like I read one input, my DFA, the state in my DFA is going to change, but the DFA can also tell the head to move to the right, move to the left. It can tell you to like erase an element, or it can tell you to like rewrite over the element and things like that. And that's much more, that's way closer to today's computers than the DFA was. Okay, so basically, the DFA, in addition to moving states, it also moves the head on the tape. And it can sort of like, it can also erase or it can rewrite. And more importantly, the head can also go back. Okay, so it can go back and read things. Okay, so it can do a lot more. And now if you think about, I mean, I'm not going to give you like a very formal description of what a Turing machine looks like because that takes a really long time. But basically, if you were thinking about accepting these zeros and ones, then I guess, I just basically want to move my head back and forth between 0 and 1. And every time I see a 0, I erase, and then I go all the way until I see like ones, and then I erase. Then, I can just kind of erase one by one the zeros and ones until they match. And if they match, then accept. If they don't, then reject, and things like that. So a Turing machine can do a lot more than what a DFA can do. Okay, But the problem is this, the Turing machines also have their own restrictions and limitations. Okay, so the most, I guess, important limitation that it has is the following. So it's called the halting problem. And this really is like the source of like all problems that we have in this field of like Hilbert's 10th problem and undecidability and things like that. So now the question is this, okay, so does there exist a Turing machine? And this Turing machine is really sort of the idea of a computer or like an algorithm or things like that that I'm going to be talking about. So every time when I ask like, does there exist an algorithm or does there exist a machine? Like I'm really talking about the Turing machine. Yeah, so, oh, sorry, yeah, I forgot to say. So the Turing machines are only more powerful if the tape and memory is infinite, and that's true. We will assume that the tape is infinite. Okay, so the memory, we're not going to place any restrictions. But I guess the point is that if you have like a single input, then it'll only use finitely many, like finite space of memory. So it's still, there's still some kind of finiteness, but depending on how long the input is, like you're not placing any restrictions on how long the tape is. Okay, so it can be arbitrarily long, but it's still like finite in a practical sense. But you know, if the memory is really large, then I guess it just means that your computer is really inefficient and it could run like for a really long time and things like that. Okay. And this does lead to another problem that we're going to be talking about. But let's go back to the halting problem because this is the biggest problem that Turing machines have. Okay, so does there exist a Turing machine? It still has inputs and outputs. Okay, so what I want is that the input, remember that I'm kind of giving the input in the integers or something, but also everything can be encoded into integers or binary. So what I'm trying to do is I'm trying to put in a pair of a program, algorithm, I guess, and also an input that I can kind of plug into the algorithm. Okay, so just imagine that this is either in like, I don't know, I mean, these should be encoded as integers. I mean, they can also be encoded as binary, but like I'm just going to assume that now they're in the integers because I'm not going to draw any machines. So they're encoded in integers. Let's say a pair of integers even. Okay. And then the output is either yes or no again. Okay. And the output is that, you know, oh, I guess I forgot to say something. So sorry, yeah. So the other problem that the Turing machine has is that also it doesn't have to terminate anymore. Okay, so there's a possibility that, you know, if you, depending on how you describe your DFA and how you have your input, the program just might run forever. So I guess maybe I should say this here. So note, Turing machines can run forever. And this is really a big problem as well. So for example, you know, maybe your input is given by just two numbers, 0 and 1. And your DFA can say something like, if you start here, it can say something like, if you see a 0, move right. If you see a 1, move left. Okay? And then it'll just kind of run forever, right? If you see a 0, move right. And now I see a 1, so I move left. And then I see a 0 again, so I move right. And then I move left again. So it can just run forever. So this is called like looping, I guess. Okay. So this kind of thing can happen. And this is a huge problem because now I can't really tell. So we just talked about how we have infinite memory. And so it could take a long time for the computer to compute and like sort of give you an answer. But now, you know, if it's looping, is it just that my computer is taking forever to compute, or is it just never going to stop? And that's a huge distinction, right? Like, so did I like make a really bad program that's just that's going to crash the computer? Or is it just taking a long time? Okay, so then this is why the halting problem is important, right? So does there exist a machine that's going to decide if I give you an algorithm and an input, is it just looping or is it actually going to finish at some point and I just have to wait? Okay, so the output is going to be yes if the algorithm doesn't loop on the input. Okay, so that means that it halts. Hence the name halting problem. Okay, and then no otherwise. If the algorithm doesn't halt on the input, then it's going to output no. Is there any way to tell whether it's looping from the outside? That's exactly what the halting problem is doing. So they want to know whether we will be able to tell whether the computer is looping or not. And this is a huge problem. And unfortunately, this is the biggest limitation of a Turing machine. And the point is that we can't. Okay. So, and this is actually sort of like even in the modern day, if you've ever thought about programming or something, sometimes you write a bad program and it just never stops running. And at some point you just have to like put a stop to it because otherwise it'll just run forever, right? So yeah, so I guess the theorem is that such a machine doesn't exist. Okay, so a huge problem. And the proof is actually pretty easy. So suppose such a machine existed. Okay, so suppose it exists. Suppose it existed. Then I'm going to build another machine. Okay, so using this, we're going to build the following machine where the input is an integer x. And this is where you have to sort of like twist your mind a little bit and like really think about it abstractly. But remember that, I'm kind of encoding my program as an integer, and I'm also encoding my input as an integer. So I have a single integer here, but I'm going to look at it in two different ways. I'm going to look at it as a program, and I'm also going to look at it as an input. Okay, so the output is going to be either yes or no again. And it's going to be yes if x viewed as a program doesn't loop on the input x. Okay, does that make sense? So this is like a little bit of a mind twister maybe. But anyway, so that's what it is. And then no otherwise. Okay, so if x viewed as a program loops on the input x, then it's going to output no. Sorry, it's not going to output no. It's just going to loop. I'm just going to make like a bad program so that my computer is going to loop. Okay. So this is the program that a new program that I want to build. And then now this is where the contradiction comes in. So let's call this h. Okay, so h is also an integer that I'm kind of encoding this program as. Then the question is, what happens if I run h on h? Okay, so h is a program and h as an input. Yes, I'm looking at x as a program and also as an input. Okay, so remember that, any finite string of characters you can write as an integer. So a program is a finite string of characters, so it can be written as an integer, but also an input is a finite string of characters, so it can be written as an integer. So given an integer, there's going to be a program that it corresponds to and an input that it corresponds to. So I'm looking at it in two different ways. Okay, so then the question is this: if I run h on h, what happens? Okay, well, either it's going to loop or it's going to not loop. So if h loops on h, then what is the output? It loops on h, so then I guess the output has to be looping. So I literally said h is not going to loop on h, but now it's looping. And then if it doesn't loop, then I guess it'll just, sorry, what does it do? And if it, sorry, I guess if it loops, sorry, I always get confused with this thing. Um, right, so yeah, I guess if it, did I screw this up? If it halts, then, sorry, let me think about this. So if h halts on h, sorry, yeah, I guess if it loops on, yeah, sorry, if it loops on input x, then I guess it has to, if x loops on x, and then otherwise. Okay, so if it if h doesn't loop on h, then I guess the output is going to be that the computer loops. Okay, and then if it loops on h, then it'll just output yes and it'll stop looping. Okay, so this is just a contradiction in both ways, right? So then either way, you're going to get a contradiction. And so this kind of a machine cannot exist because, it literally just logically doesn't make sense. Does that make sense? Um, Sorry about the confusion. I always get confused with this thing, but I just want to make sure that you guys understand this. Questions? Okay, so I'm gonna assume that you guys understand this halting problem and sort of the solution to the halting problem because it's gonna come back. So if you guys have questions, please ask me. Okay, so then let's go back to Hilbert's 10th problem. Okay, so now we're back to Hilbert's 10th problem, which was, if I input a polynomial into a computer, it's either going to answer yes or no, depending on whether it has an integer solution or not. That was the exercise that we were doing at the beginning of the talk. And now we actually have an idea of what a computer is and what kind of limitations this computer is going to have if you define the computer in sort of like the most reasonable way possible. Okay, and this halting problem is going to be a huge thing because this is what makes Hilbert's 10th problem impossible. Okay, so the theorem due to Matiyasevich, I think in the 70s, and it was, and he sort of did the really big step, but basically this team of researchers, Davis, Putnam, and Robinson, I guess the Robinsons, they were, I guess, husband and wife mathematicians, but this is the wife, Julia Robinson. Okay. And yeah, so I guess, so they had basically done everything and they were missing just one step, and Matiyasevich managed to sort of plug in that one step. So that's why everybody gets credit here. So they basically showed that no such machine exists. Okay, so what that means is, people say this, that Hilbert's 10th is undecidable. That is, if you give me a polynomial, then I won't be able to decide whether it has an integer solution or not in any algorithmic way. Like obviously, we've decided that lots of integers, lots of polynomials had integer solutions before, but it was a very ad hoc, and that's sort of the best you can do in some sense. What? Okay, sorry, I don't know. Okay, typo. Okay, if you have questions, keep typing into the chat. I am reading the chat. Okay, so I want to give you a sketch of the proof. And so I guess there are sort of like two parts to this proof. So the first thing that I'm going to do, okay, so question, what's to say that there isn't a more powerful class than Turing machines that can solve H10? I guess it depends. So I guess that's why people are thinking about these like quantum things and things like that. But I think this is, I mean, I'm not an expert in the computability theory, but I think this is sort of like the Church Turing thesis or something that basically says that most modern, like all the modern computers are equivalent to the Turing machine or something. I think people, yeah, oh, okay, yes, somebody said this. Yeah. So yeah, I think basically like you're able to prove in some like very fundamental way, just kind of thinking about all the different operations that a computer can do, that they're actually equivalent to the Turing machine. Okay, we're not gonna get to ZFC being inconsistent, but yeah, so somehow like I guess we kind of know that Turing machine is the best we can do. Okay. Yeah, so then I guess I want to first start by sort of rewording this Hilbert's 10th problem in a different language that's actually going to allow us to kind of prove that this is undecidable. So the first step that I want to do is a reduction into a more sort of like manageable language. Okay, so what I'm going to do is I'm going to define and compare two different types of sets. Two types of sets. Okay, so so the first definition is going to be, so I'm looking at subsets of the integers. Remember that everything can be encoded into the integers. So I'm just kind of taking some subset, like any set, any subset really can be encoded into this. So I'm going to say that this is computable if there exists a program or algorithm such that the input is an any integer and output is either yes or no. And the output is yes if x is an A and no otherwise. Okay, so this is sort of like the most simple thing that you can do. I guess I'm just basically asking, oh, sorry, I don't know how to do this. but I'm just basically asking, the thing that we've been asking about for the entire talk, right? Does there exist a program that does this or not? And then the other type of set that I want to talk about is called Diophantine. And this is a little bit trickier. So if there exists a polynomial P. And it has many, many different variables. I'm just going to sort of put a special emphasis on the first variable, and everything else I will just kind of say like, some kind of an X. And it has integer coefficients such that I can define A using this polynomial. So it's going to be the set of integers X in Z. Oh, sorry, I can't use X anymore. Set of integers, let's say little a in Z, such that there exists some X. I don't know if you guys have seen this notation before. It means there exists some kind of an X. Maybe I will use Y or something. So there exists a bunch of integers Y in Z to the power of, let's say, N, such that P of A comma Y is equal to 0. Okay, so it just means that I'm looking at a set of integers such that, if I plug in that integer into this polynomial, then does the rest of this polynomial have an integer solution or not? Okay, and if it does, then it belongs in A, and if it doesn't belong in A. So somehow it really kind of encodes this idea of Hilbert's 10th problem type thing. Okay, so there's the computable aspect, like, the computer aspect, and there's sort of like the algebraic aspect that you're thinking about. All right, so then what is the key fact? Why is this a reduction? So like the really important fact is that if there is a Diophantine set that is not computable, then Hilbert's 10th is undecidable. Okay, and here's the quick proof. So suppose again for a contradiction that there was the computer program that will kind of tell me Hilbert's 10th. Okay, so suppose there was a machine for H10. So suppose that there was a program such that if I input a polynomial, then it'll say yes or no. Okay, so then I claim that whatever this set is, so suppose that there is a Diophantine set A that is not computable, then I claim that A is in fact computable. Okay, and that would be a direct contradiction because I literally said if there is a Diophantine that is not computable, then Hilbert's 10th would be undecidable. And if it were decidable, then any Diophantine set is going to be computable. That's what I'm trying to say. Okay, so then the input is going to be any integer, right? So I'm going to take an integer n, and here's the black box. And the question is this, right? I mean, this is exactly what we've been talking about. So the question is going to be, does the polynomial p, sorry, that came out weird. So p of n comma x have a solution where I've like already plugged in n. So then now this is a polynomial only in x. And if this thing existed, then it should be able to say either yes or no. And if it says yes, that means that n is in A. And if it says no, then n is not in A because that's literally the definition. Okay, so then that means that A is computable, which is a contradiction because I literally said there, if A is a Diophantine set that is not computable. But if Hilbert's 10th were decidable, then every Diophantine set is computable. So there's a contradiction. Okay, does that make sense? So now we're just basically trying to, I guess, compare these two types of sets, and we're trying to find a Diophantine set that is not computable. And if we can do that, then we basically solved Hilbert's 10th problem. Questions? No questions? Hopefully I didn't lose all of you guys. So now the goal is to compare, I guess, computable sets versus Diophantine sets. Does that make sense? So that was the reduction. So instead of, kind of asking about does there exist a computer, which kind of seems a little bit daunting from like the mathematical point of view, now we're kind of, trying to write this in a more mathematical way. And then the second part of the proof is that in order to compare these computable and Diophantine sets, we're going to introduce a third type of set that's going to kind of allow us to like really make the comparison because it'll be much easier to compare between the two. Okay, so introduce a third type of set. And this is the definition. So if I have a subset of the integers, we're going to say that this is listable if, okay, and this is really kind of encapsulating this idea of a Turing machine. So if there exists a Turing machine so remember that Turing machine can kind of run forever, right? So if a Turing machine exists such that if, well, I guess this Turing machine has to prints out precisely the elements of A eventually. Okay, but the problem is that, maybe it'll print out, suppose that 1 is an A or something. Maybe this machine will print out 1 like 20 billion times, and then it'll print out the next one or something, right? So you just don't know how long it'll take to like really print out every element of A. A also could be infinite. So you just have to kind of accept that this machine is just basically going to run forever. And so it's not quite computable because you can't decide from this machine whether whether a particular element belongs in this set, because if the Turing machine hasn't printed it out. Okay, so has it not printed out this number because we just haven't made it run enough? Or does it just not belong there? So it just like already decided that it wasn't, well, I guess it doesn't know, but is that why it's not being printed? Okay, so this is like slightly weaker than computable. And yeah, so then I guess this is a third type. And so what I'm trying to do is I'm trying to compare the listable sets to the computable sets and Diophantine sets. Okay, so first, so there are lots of comparisons that we have to make. So I claim that a computable set is always listable. Do you guys see why? So a set A can be listed after an infinite amount of time, and it is still listable. Technically, yes. So I guess if you look at a specific element of the set, then I guess at some finite time it has to be printed. But of course, the set itself is infinite. So you're essentially just letting it run forever. But if it were in the set, at some point it will be printed. Okay, but if it's not in the set, then you just don't know. Okay, so I claim that computable sets are listable. Do you guys see why? Can you come up with a Turing machine that'll print out elements of this computable set eventually? I guess it's pretty easy, right? Because the computable set already kind of comes with a Turing machine that decides. Yeah, just go through all the tuples and check with the machine. Like I already have a machine here. A computable set literally comes with a machine. Okay, so if n is in this set, computable set, like A or something, then print it. Because I actually already know if it's in the set or not. And if n is not an A, then don't. I can't even call it like an algorithm. I guess you're just literally using the same machine. So this is really trivial. Okay. And I also claim that Diophantine sets are listable. Okay, so remember that a Diophantine set is just basically the set of A's in Z such that there exists an X, or I think I used Y or something before, a bunch of integers such that some polynomial AY is equal to 0. Okay, so a Diophantine set looks like this, and the algorithm is actually kind of tricky, okay? And this is why, like, the Diophantine sets can't just be computable. Okay, and question, can you please display the first point again? Which first point? This thing? I don't know what you mean by the first point, so I'm not sure how far to go back, but hopefully this is what you were thinking of. Okay, sorry. Okay, so then the algorithm is going to be the following. So basically, I want to know whether does 1 belong to A? Okay, so I guess I'm just basically going to check whether there exists the y in -1 to 1 to the power of n. So like, just basically, I want to know whether one belongs to the set. So then I'm going to plug in 1 and I have a polynomial. So I'm going to check for all the y's between -1 and 1 and see if any of these things give you a 0 when you plug these things in. Yeah, exactly. So this is what Marcus is trying to say. And maybe why can't we use our Turing machine for Diophantine sets? to list the Diophantine set? Well, because the Diophantine set doesn't come with a Turing machine. It like literally the only thing that defines a Diophantine set is a polynomial. So we don't have a machine. I'm just basically trying to build a machine, and it's only going to be listable. It won't be able to decide whether an element is not in this set. Okay, so that's what I'm basically trying to say. So I'm trying to check why between -1 and 1, like just basically plug in all of these things because there are only finitely many of them into here and see if any of them make it 0. Okay, so if any of them solve the equation P, then print 1. Otherwise, keep going. What am I doing? So now I'm going to test whether 1 or 2 is an A, and I'm going to check Y between -2 to 2. Okay, and if I can kind of find the proof, sorry, this should be N. And if I can find a proof that any of them actually is an A, then I'm going to print. Otherwise, I'm going to keep going. Okay, so if any solve the equation, print. Otherwise, now I'm going to test 1, 2, 3. And then I'm also going to try from -3 to 3. Okay, so that in this way, if any of these things solve the equation, then you will kind of reach it in a finitely many steps. But if it doesn't, if it's not going to solve the equation, then you just won't know. It'll just run forever, and it'll just never print it. Okay, so this is listable, but this machine doesn't give you any proof that it's going to be computable. Okay, and also I know that listable is not computable. It doesn't imply computable. So that means that there are listable sets that are definitely not computable. Okay. Why does listable not imply computable? Well, we're going to come back to the fundamental problem with the Turing machine. So remember that there is this halting set. Okay. So recall the halting problem. So yeah, I guess halting set was, I guess, a program and an input. Such that P halts on the input. Okay, and I claim that this set, which you can also write as a subset of the integers. Okay, so you can write it as, for example, 2 to the program, 3 to the input, or something like that. So I claim that this set is not computable, but it is listable. Okay, so we've already shown that this is not computable because that's literally the content of the halting problem. There does not exist a program that's going to decide whether, that's going to decide whether a program stops on the input. So this is obvious. This is from our proof of the halting problem. And then it's going to be listable because a program is finite. So I'm going to do something very similar to what I did with the Diophantine sets. I'm going to take an input. I'm going to run it in the program. I'm going to, and I guess, I'm taking like a, input as 1 or something like that. And I'm going to run it for like a set number of times, a set number of steps. So, every time, like, remember that a computer just kind of moves around the state. So, I'm going to say like, okay, so if it doesn't stop, or if it doesn't stop in like 10 steps, then, just put it aside for now and then, come back to it. And now next time I will try like 20 different programs, but, I'll do it for 20 steps and so on. Okay, so some kind of a diagonalization argument will kind of tell you that it is actually listable. Okay, so this is like an exercise, but you just basically have to use like a very similar idea as this thing here. Okay, and then I guess the really important thing, so far, what have we shown? So I guess, let's go back here. So what have I shown? So the listable sets contain all the computable sets and all the Diophantine sets. Okay, but I guess I've shown that the listable sets, okay, so I know for sure that if this is listable, then the computable sets are smaller. Okay, and there definitely exists like elements that are not computable. Okay, but the problem is, I don't know whether Diophantine sets and listable sets are exactly the same. Remember that if we wanted to solve Hilbert's 10th problem, I was looking for a Diophantine set that is not computable. Okay, so then the DPRM theorem, what they did was to show that listable sets is exactly Diophantine. Okay, so this was also, it can be replaced by Diophantine sets, which means that I found a Diophantine set that is not computable. And that really kind of goes back to this reduction that we were talking about before. I don't know how to go back. So, if there is a Diophantine set that is not computable, then Hilbert's 10th problem is undecidable. And what their theorem just basically kind of proved that there does exist a set like this. And it's kind of cool because I guess you can literally just like write down the set from the halting set or something like that. So yeah, so then all of this basically says that Hilbert's 10th is undecidable. Okay. And the way you kind of prove this is really cool as well. They actually wrote like a really long book. I think it's like several hundred pages or something, actually just kind of showing that listable sets is Diophantine. And basically, you just look at every, I guess, operation of the computer and you try to write that as polynomials, I guess. So yeah, I guess it's kind of hard to describe in a short amount of time. So I will just kind of leave it there. A good exercise is that you can also do this using DFAs as well, because DFAs are just a special case of the Turing machine. And with the DFAs, I think you can actually kind of write these using polynomials and not without like it being like too painful. Okay. So yeah, then I guess this is sort of the idea of, how you kind of try to prove Hilbert's 10th being undecidable. If I had more time, I would have talked about, what happens in other cases. So for example, maybe you could ask for polynomials that have solutions mod n for some integer. And that's actually kind of trivial if you think about it, because there are only finitely many things that you can plug into the polynomial. So if I were looking for solutions, a program that decides whether a polynomial has solutions mod n, then it does exist. Okay. If I were asking for a polynomial, that decides whether a polynomial has a solution in C, then it exists. The program is that you can just plug in, you can just output yes for all of these things unless the polynomial is constant. Does it carry over to the p-adic numbers? It does not, because p-adics have what's called the quantifier elimination. So in fact, you can decide for the p-adic numbers. And is there a different result if the polynomial only has one variables? And yes, we can decide. And I guess it's like, I don't know what it's called, but like, depending on the coefficient of the leading term and the constant term, there are only finitely many lists of like even rational solutions that the polynomial can take, and then you can just plug those in. Yeah, I don't know what RRT is, but that's probably what I was talking about. Rational root theorem, I guess that's what it is. Yeah, okay. So yeah, you can use that. If the polynomial was linear, then you can use like, the Gauss-Jordan elimination and things like that. So there are like lots of different variants that you can do. So yeah, and I guess the big thing that I would have talked about if I had more time is that in fact, this question is open. So we have no idea whether there exists a machine or not that decides whether a polynomial has rational solutions. And this is like a big problem for the number theorists, because that's literally what I care about. Like I look for rational solutions to specific polynomials. And I guess that's what keeps my job, because people suspect that there does not exist a program that can decide whether something has a rational solution or not. Typically, I think it's much harder to check for rational solutions than the integer solutions. So if it's already impossible for integer solutions, it should be undecidable for the rationals. We don't know how to prove it. There's some partial results, partial attempts that people have made towards this, but I guess I'm out of time, so I won't talk about this, but maybe Marcus will. So yeah, so I guess that's it. If you guys have any questions, I'm happy to take questions now. What classes is this decidable for? Yeah, those are like there's a specific list. But I don't know if you can kind of describe them all in one sentence. So people really just kind of take a specific variant and they really have to kind of prove whether it's decidable or not. But the really interesting thing is that if it's undecidable, everything traces back to the halting problem. So halting problem is sort of the root of, I guess, all problems in this field so far. It's possible that there are some other rings where halting problem is not going to be enough, but it's still undecidable. But as far as we know, everything is about the halting problem. Are there any results in abelian varieties? What do you mean? Oh, like whether an abelian variety has a solution or not? So I guess I know about elliptic curves. So for integers, I think there's like Siegel's theorem and like sort of like the related I don't know, like some explicit results. I forget, like Nagel-Lutz theorem, I think literally like gives you a finite list of integer points that it can have. For the rational points, I think it's much harder. What are the recent progress over the rings of integers? So now we know that the rings of integers are all undecidable. Yeah, 2025. This is by what's his name? Koymans and Pagano. So now we know that the rings of integers are undecidable. Before we knew it, subject to some specific conjecture in number theory that I'm not going to talk about. But now we know this unconditionally. Um, yeah, so I don't know what more I can talk about now, but yeah, if you have more questions, you can either speak or type more on the chat, and I'm happy to answer more.
Yeah, thanks for a great talk. And other questions?
Does my work relate to this? Yes. So I thought about sort of trying to understand what happens for the number fields, which are generalizations of the rational numbers. So so I guess what I was trying to do is, can I actually find some kind of an algorithm that's going to reduce the number field or the rationals to the integers and things like that. Um, I don't know. I mean, it's some kind of a partial thing. And another thing that I tried to do is, there are lots of kind of things between the integers, which we know are undecidable, and rationals that are open. So for example, if I allow a specific, so I'm looking for rational solutions, but suppose that I'm only allowing specific prime numbers to divide the denominator or something, then is it decidable or not? And the question is like really complicated. So I think one of my results will say something like, if I allow very few primes into the denominator, then it can still be open. It can still be sort of equivalent to Hilbert's 10th over Q, and things like that. So, there's a lot of effort in bridging, I guess, the integers to the rationals and sort of more generally the rings of integers to number fields and things like that. I've thought a lot about that. You can also think about sort of function fields where you allow some variables into your solutions. And I've thought about that. I guess at some point there will be a paper out showing that specific function fields are undecidable, but I'm working on that now. So yeah, I mean, a part of my work relates to this. I wouldn't say that this is the main thing that I do, but definitely it's something that I'm interested in. Okay, any other questions? Yeah, I don't know if somebody's just typing like a really long answer or nobody's typing and we're done.
Yeah, yeah, probably no more questions. So then, yeah, let's stop here. So thanks again.
Yeah, thanks for having me.